morning, everyone. So, only few people are there for the ESC. Okay, so now the last word for the EAC is flow measurement, and this flow measurement is very important for the EAC people. Every year you can expect a question from the flow measurement in EAC. Okay. Now let's see. So now let's see the new chapter. Flow measurements are flow through orifice, mouthpiece, notches, and weaves. Notches and weaves. Okay. From this chapter in ESC, 1 to 2 questions. 1 to 2 questions, and this is very important for the IES mains also. This chapter is important for the mains also. So this is the flow through orifice, mouthpieces, notches, and wears. And what are these? These are nothing but the devices to measure the fluid, to measure the flow rate. So here the main purpose, the objective of this chapter is to measure flow rate. To measure flow rate. So I hope you may have heard about this type of devices. Yeah. So now let's see. So I hope you may have heard about these devices known as orifice, mouthpiece, notches, and wears. Now let's see what are these devices again, and how you are going to measure the flow rate by using these orifices, and how this chapter is going to be important for the examination, and what type of questions can be expected here. Okay. So first of all, let me go with the orifice. Let me go with the orifice. So here. First one, orifice. What is meant by orifice? Orifice is a small opening. Orifice is a small opening provided at the side or bottom of a tank. At the side or a bottom of a tank. Or simple, you see, for every means in our house, overhead tank would be there. Overhead tank would be there. For the overhead tank, on the side of the tank or bottom of the tank, we used to keep some tap. Yes or no? And when I open the tap, water will come. And that opening for the tap, in order to fit the tap, you have provided one opening before the construction, means before fitting of the tap. Yes or no? So whatever the tank you take, overhead tank, on the sides or at the bottom, we keep one tap like this. Yes or no? And whatever this opening that you have provided over here to the tank, and that is known as orifice. That is known as orifice. Whatever this is, whatever the opening that I provide to the tank, this is a cross section I am showing you. This is a cross section. So whatever the tank, overhead tank, if you are going to provide a small opening at the sides or at the bottom, and to measure that flow, we are going to call this opening as an orifice. This opening as an orifice. And whatever the tube I am fitting over here, right? This tube is known as a mouthpiece. Whatever the tube here fitting is known as a mouthpiece, and this opening is known as a orifice. So the opening where you are allow the flow is orifice, and the pipe that you are fitting to this opening is known as a mouthpiece. Okay. So first of all, what is the definition of the orifice? What is the definition of the orifice? So the definition of the orifice is, it is a small opening provided at the bottom side of a tank. Side of a tank. It is a small opening provided at the bottom or a side of a tank to measure flow rate in tank. So how much flow rate is passing in the tank, you are going to measure by using this orifice. So now let's see how does it looks like that orifice. Let me take the cross section of our tank. You see. So what I'm drawing here is a tank, my dear. Yes. Okay. So let's take it as a tank over here, and now whatever the level of water, whatever the level of water in the tank is, let's take this is the level of water in the tank. Okay. Now whatever this is there on and this is known as orifice. Whatever this opening is there, right? This opening is known as a orifice. Now let me take out that. Okay. So here whatever the opening, whether it is a circular opening or a rectangular opening or square opening. So generally we prefer the circular orifices only. Yes. So mostly we prefer the circular, and this is known as orifice. This is known as a orifice. So what is orifice? It's a small opening provided at the sides or at the bottom, where we are going to see that one as an opening, and the cross section of the opening, it can be circular, it can be rectangular, it can be triangular, it can be square, but generally we used to take that one as a circular. Okay. And now if from the center level, you know, this is a center level of the water or not? So whatever the height of water that is located from the center level, whatever the height of water that is located from the center level, let's take that is a head of water as a H. This is a head of water H, and let's take a D is the dia of orifice. Let's take D is the dia of the orifice. Okay. So now you see, if D is the dia of the orifice, D is dia of orifice, and H is head of water above center line of orifice. Above center line of the orifice. So if D is the dia of the orifice and H is the head of water above the center line of the orifice, then we can say whenever this H is going to be more than 5 times of D, when the H is more than 5 times of D, we call it as a small orifice, where D is very less than H. And when H is going to be less than 5 times of D, we call it as a large orifice. We call it as large orifice. And generally we prefer the small orifices only. So generally we used to prefer the small orifice only. Now, if H is the head of water from the center line of the center line, if H is the head of water from the center line and D is the dia, based upon that we are going to say whether it is a small orifice or large orifice. Now let's take this figure once again. So from this figure, now I have shown you what is the orifice looking like. Now you can see this is nothing but a sharp edge or not. Whatever here, everything I am representing. So whatever here, this is a sharp edge orifice. Sharp edge orifice. So this is a cross section view, and is means for the cross section view of the orifice, this is looks like this. Okay. So now based upon this dia and H, now let's see how we are going to measure the flow rate. How we are going to measure the flow rate. Observe here carefully. Now you see when the flow is going to be emerges out, when the flow is going to be emerges out, due to the sharp edges, the contact of the flow is going to be minimum. While the flow is emerging out through the orifice opening, due to sharp edge, the contact of the flow, due to sharp edges, the contact of the flow is less. When the contact of the fluid is less with the surface, then the frictional loss is also lesser. The more the contact with the surface, the more the boundary friction, the more the resistance, lesser the contact. So first what happens is when the flow is emerging out, you see what is going to be happen is first the flow area is going to be decreases. First the flow area is going to be decreases. For that, better understanding of that. What I do is, so while the flow is coming out, so when the flow is coming out, now first the flow area will decreases. The flow area will decreases and forms a minimum cross section and that is known as a vena contracta. I hope you know what is the meaning of vena contracta. We have been discussed in the case of the open channel flow also. So what is the vena contracta? The vena contracta is a section where the flow area is a minimum. So now here this is known as a vena contracta. Vena contracta. And from here onwards, the streamlines are going to be parallel to each other. From here on, you see earlier the water level is going to be, the flow area is going to be decreases, and at vena contracta it is going to be minimum. And beyond vena contracta or from vena contracta, the streamlines are going to be parallel, and the jet is going to be emerges out like this. The jet is going to be emerges out as a parabolic motion, with the streamlines are going to be parallel to the. So now this is how the jet is going to be emerges out. This is how the jet is going to be emerges out. This is nothing but a jet. And what is the area of jet? What is the area of jet? What is the actual area of the jet? Is it the area at the opening or area of the vena contracta? You tell me. What is the actual flow area of the jet? The actual flow area of the jet is not at the area of opening. You know, this is nothing but the dia. Here, this is going to be the dia D. And here, this is a vena contracta. Now, what is vena contracta? Vena contracta. Vena contracta is a section at which flow area is a minimum. Flow area is a minimum. Okay. So now, as D is going to be the dia of orifice, area of opening small a is represented with a pi by 4 d square. Pi by 4 d square. Okay. Whatever the area of the opening small a is nothing but the pi by 4 d square. Okay. So now keep that in your mind. This is the area of the opening. Now, in this case, while the area is going to be forms like this, now what is the actual area of opening? What is the actual area of the opening? The actual area of jet is equals to area at vena contracta. area at vena contracta. So the actual area of the jet while it is emerging out, actual area of the jet emerging out is going to be area at a vena contracta. So the area of opening is small a, but actual area is not a small a. Yes or no? Because due to vena contracta, the flow area will decreases. So where the flow area is minimum, from there the jet is going to be emerges out with that area. Now let's see the analysis over here. Similarly, whatever the velocity, let's take a V is the V theoretical velocity. If I represent just as a V, theoretical velocity, yet orifice opening. Yet orifice opening. So theoretical velocity at the orifice opening, and V actual velocity is velocity of flow at vena contracta. At vena contracta. Now, you see, observe here what I am going to do the analysis. As a flow emerging out at vena contracta from orifice. As the flow emerging out from the orifice is not supported by any, see, this is not supported by any, whatever the flow here, this is a completely in a atmospheric pressure. So while the whatever the flow coming out, this is not going to be supported by anything. There, then whatever the pressure over here at the top and the bottom, this pressure is known as atmospheric pressure. This pressure is known as atmospheric pressure. So flow emerging out from orifice, this point is very, very important. Flow emerging out from orifice is not supporting by any. So pressure above and below is atmospheric pressure. Okay. So now let's take out that once again. Whatever the figure. Okay. Now same thing. So now I am going to do the analysis. See, what I have done here is I am explaining the topics, terms. So there is an opening known as a D, and there is a vena contracta. But what is the actual area of the jet? Actual area of jet is nothing but area at the vena contracta. And what is the actual velocity? Velocity of the flow at the vena contracta. And as the flow emerging out from orifice is not supported by any, pressure above and below is atmospheric pressure. So now let's see this figure once again. Now I am going to apply a Bernoulli's equation by taking this as point number 1. This is going to be point number 2. This is going to be point number 2. So by applying Bernoulli's principle, Bernoulli's yet 1 and 2. You know that total head at any section is going to be same. So P1 by rho g plus V square 1 by 2g plus Z1 is equals to P2 by rho g plus V2 square by 2g plus Z2. And let's assume the datum as a center line of orifice. Let's assume the datum as a center line of the orifice. So now datum is a center line of orifice. Now you tell me at 1, just now I told you, see, at 1, what is the pressure? This is a free water surface or not? At 1, this is a free water surface. As it is a free water surface, you know that at the free water surface, the pressure is going to be 0. At the free water surface, the pressure is going to be 0. And whatever this velocity, this is nothing but approach velocity, where VA is approach velocity. And in the case of the small orifice, the height of the approach velocity is going to be very large. So when the height is going to be very large, generally at a water surface, so we are going to neglect the approach velocity. Approach velocity, and HA is general, VA square by 2G. Approach velocity head. So generally we neglect that. And now, what is the datum over here? Please tell me. What is the datum over here? Z1. What is the datum? So for this one, what is the datum? Datum is nothing but H. Yes or no? That's it. So this is going to be the H. At a water surface, pressure head is going to be 0. And at a free water surface, approach velocity head is neglected. And what is the datum? From here to the datum, H. So similarly, on the other side, you know, whatever at a point to just now I mentioned the atmospheric pressure only, right? Whatever the pressure here is nothing but the atmospheric pressure only. So again, this is also going to be 0 because this is atmospheric pressure. And here also it is going to be atmospheric pressure. So we are going to take it as 0. And now V2 square by 2G is there. And what is J2? J2 is also going to be 0 because the point 2 and the datum both are coincides. As a point 2 and datum both are going to be coincides, then can I say the datum and 2 as section point 2 and the datum coincide. J2 is equals to 0 and P1 is equals to P2 is equals to atmospheric pressure. So when the atmospheric pressure, then the gauge pressure is going to be 0. You know these things earlier. So gauge pressure is equals to 0. And now from this, can I write H is equals to V2 square by 2G and V2 is equals to root of 2GH, and where that V2 is nothing but velocity at the orifice opening. Is it a theoretical velocity or actual velocity? I told you. What is actual velocity? Velocity of the flow at vena contracta. What is actual velocity? Velocity of the flow at vena contracta is actual velocity. But the theoretical velocity is the velocity at the orifice opening. So I can write this one as V is equals to root of 2GH. So I hope you remember this equation. This is also known as the Torricelli's equation. And this equation holds good for every flow. See, I am going to apply everywhere. What I have done is just simply, this is the starting of the flow and this is the flow emerging out. This is the starting of the flow and this is the flow emerging out. So this is the actual, this is the velocity at the orifice opening. And now, based upon this, once I know what is the area of the opening A, and once I know the area of, so what is the velocity V, now we are going to find out approach velocity is not very large. Why E is negative? Approach velocity is lesser. This head is going to be more. Whatever this H is more, na? Whereas as this H is going to be more, see when the flow is going to be approaches, means in the tank this is still water, right? In the tank this is going to be a still water. So at the still water means velocity of flow is going to be 0. But while the flow is emerging out, then see in the tank the water is going to be still. So at the top velocity is 0. But while the flow is emerging out, it must be having some velocity. Emerges out means it must be having some velocity. Okay. Now let's see. So how I have done this one. This is nothing but V2 velocity at orifice opening and A or area of the opening. But is it actual velocity? No. Is it actual area? No. So now there we are going to see the help of the coefficients. Coefficients. Due to sharp edges and losses. Due to sharp edges and losses. So the actual area is not at the area at opening. Actual area is not equals to area at opening. Area of orifice opening. Actual area is equals to area at vena contracta. Area at vena contracta. So definitely there must be some coefficient, and that coefficient we are going to represent as a coefficient of contraction. I hope you remember the coefficient of contraction, right? So what is the coefficient of contraction? Area at vena contracta by theoretical area. What is nothing but area? Theoretical area. Theoretical area of orifice opening. So let me represent this as a small a. So now from this CC is equals to area actual by small a. And what is the actual area now? The actual area is equals to CC into A. CC into A. So area of the jet at the vena contracta or area of the flow at vena contracta by theoretical area of opening, orifice opening. Typical area of orifice. Okay. So what is the area of the orifice? A. And generally the CC is going to be 0.62. CC is equals to 0.62. So what is the quotient of contraction? The coefficient of the contraction is the actual area by area of the orifice. Our actual area is equals to CC into A. Okay. Now see, this is one. And second one is coefficient of contraction. CC coefficient of contraction CC. So now similarly, let's see, coefficient of velocity represented with the CV. Coefficient of velocity represented with the CV. Again, area, sorry, velocity of jet at vena contracta to velocity of jet at vena contracta to theoretical velocity. Theoretical velocity. So what is our CV? Now V actual means V at Veena contractor by V theoretical as a small v. So now here V actual is equals to V CV into yes V CV into V. Remember, whatever the pressures we are taking, see this pressure, whatever the pressure is gauge pressure only we take. After all the open channel flow, you are asking this question. Have I took the pressure in the open channel flow? Tell me. Have I taken anything regarding to the pressure in the open channel flow? No. Why? At a free water surface, what is the pressure? Atmospheric pressure. And what is the meaning of atmospheric pressure? Gauge pressure is zero. So these pressures are nothing but the gauge pressures. Whatever the measurement of the pressures are nothing but the gauge pressures. Okay. So here, these pressures are nothing but the gauge pressures. So we have to take them as zero. Okay. Now, so V actual. So generally, this for sharp edge. For sharp edge orifice, CV is equals to around 0.95 to 0.99. CV value is going to be around 0.95 to 0.99. Okay. So this is the CV value here. So first of all, once we know this CV now you see these actual and these are theoretical. Yes. So finally, what we require is a discharge. Finally, what we require is a discharge. So actual flow rate. Actual flow rate. So Q actual is equals to Q actual is equals to Q actual is equals to actual area of the jet into actual velocity. So the actual discharge Q is equals to area of the actual CC into A into CV into V. V is nothing but root of 2GH and Q is equals to CC into CV into A into root of 2GH, and this CC into CV we are going to call one more coefficient known as a coefficient of discharge. And now this Q is nothing but a CD into A into root 2GH. This is the actual discharge. This is the actual discharge. So what is the actual discharge? So actual discharge is nothing but CD is equals to A into root 2GH, and where CD is known as coefficient of discharge. Coefficient of discharge. Okay, and this CD can be written as a CC into CV, right? Whatever the CD is nothing but CC into CV. So which is nothing but actual discharge by theoretical discharge. Actual discharge by theoretical discharge. You know what is the meaning of CC? Actual area by theoretical velocity, theoretical area. CV, actual velocity by theoretical velocity. So actual area into actual velocity, actual discharge by theoretical area into theoretical velocity, theoretical discharge. So now, you know this CD and how to find out the CD, sir? Once I know the CV, then I can find out the CC. Then I can find out the CD. Sir, what about the area of Veena contractor, sir? That you can find out the Veena contractor at the opening space. So now let's see how to determine this CV. And once you know CV, so final formula, how I started, how I have started. You see, what is the objective here? To measure the flow rate. And finally, this is the flow rate passing through the orifice. Flow rate passing through the orifice. Okay. Similarly, so now determination of CV. Once I know CV, then only I can find out the CD value. Okay. So now you see, this is a Veena contractor. And from here only the jet is going to be emerges out like this. So here only the jet is going to be emerges out like this. Yes or no? So now you know from the basic kinematics, let's say that jet is going to be travel a distance of x, and from the center line the jet is going to be travel a distance of x and a vertical distance of y. So the jet is going to be travel a distance of x and a vertical distance of y. From kinematics, whatever the distance traveled by this jet, whatever the distance see this is jet, right? This is jet. Whatever the distance traveled by this jet, x is nothing but so the distance velocity into time. Whatever the distance, see when the jet is going to be emerges out, it must be having, see from the Veena contractor, this just be having some velocity, and you know that velocity is nothing but the actual velocity. Yes or no? So actual velocity. Okay. Now you see this is a V actual. You keep that as okay. And whatever while it is falling down, whatever the depth it is going to be falling down, that is going to be half gt square. Means the whatever falls down by means of the gravity or not. So this is a parabolic path. It travels a horizontal distance x and a vertical distance y, and x is nothing but v into t, and y is equals to half gt square. So from this we can write t is nothing but x by v. Okay. So now here y is equals to half g into t value x square by v square, and you take this v square to the other side, then v is nothing but square root of gx square by 2y. Square root of gx square by 2y. And this v, is it actual velocity or theoretical velocity? This is the actual. Why? Because I am taking from the Veena contractor. You see, this is nothing but the Veena contractor, right? So whatever, this is nothing but Veena contractor, and the velocity of the jet is nothing but the actual velocity. The velocity of jet is nothing but actual velocity. Is nothing but at Veena contractor. So that is nothing but root of gx square by 2y. I hope you understood this from kinematics. So x and y, now you substitute. So what we required is CV, right? And what is CV? Actual velocity by theoretical velocity as a v, and CV is equals to, what is actual velocity now? Root of gx square by 2 by root of 2gh. Then CV is equals to square root of gx square by 2y into 2gh. So anyways gg will get cancelled. Then root x. So x by root of 2hy. This is how we are going to find out the coefficient of the velocity. This is how we are going to find out the coefficient of the velocity. So is the velocity actually just before the Veena contractor? No. After the Veena contractor only the velocity is going to be actual. After the Veena contractor only the velocity is going to be actual. And keep that in your mind. Don't think the variation is too much. You see, what is the value of CV? What is the value of CV? 0.95 to 0.99 or not? What is the value of CV? 0.95 to 0.99. So, which means the actual velocity is going to be almost 0.95 times of the theoretical velocity. Okay, sorry. This is 4. This is 4. not 2, that's 4. This is from the basic kinematics, my dear, whatever the x and whatever the y, from the basic kinematics. Don't ask me your physics now. From the basic kinematics, okay? So this value, this is very, very important, especially for the ESC prelims, my dear. This is important. What is CV? Quotient of a velocity. And once we know the quotient of velocity, then we can find out the CD value. CD is nothing but CC into CV. There is one more coefficient. I hope you understood these coefficients. So this is quotient of contraction, quotient of velocity, and here it is going to be the quotient of discharge. And there is one more quotient known as coefficient of resistance. Represented with CV, coefficient of resistance represented with CV. So whatever the loss of kinematic energy during the flow through an orifice. So how much kinetic energy is going to be lost? Loss of kinetic energy of flow through orifice to actual kinetic energy. So now CV is nothing but theoretical kinetic energy minus kinetic energy at actual by kinetic energy at the actual. So you know that, you observe what is the meaning of this one is, you see, while the flow jet is going to be emerges, this here theoretical velocity, and what is the typical velocity? V. And by the time it reaches, what is the velocity? Actual velocity. So how much energy is going to be losses? How much kinetic energy is going to be losses from the opening to the vena contracta? So from the orifice opening to the vena contracta. So whatever the velocity here is V, and here is going to be the V actual. So during this process, how much energy is going to be lost? Now, you know that kinetic head is nothing but V square by 2G. So CV is nothing but V square by 2G minus V actual square by 2G by V actual square by 2G. So everywhere the 2G will be gets cancelled. Now can I write CV is equals to V square minus, what is V actual? What is V actual? CV into V, right? CV into V square by CV into V square. CV into V square. Now from here onwards, okay. Quotient of velocity. Now, can I write this one as a V square minus CV square V square by CV square V square. So why I am taking this one? This is not okay. This is not CV. I'm using it as CV, right? Sorry. Coefficient of resistance means CR. Coefficient of resistance is a CR. Okay. I am not going at all any fast. Am I going fast over here? No, not at all. I am going fast. I am just explaining the terms. So this is a jet. Okay, now what is happening? What is the meaning of coefficient of resistance, please? See, when the flow is going to be starts from the orifice, when the flow is going to be starts from the orifice, so at the orifice, the velocity of a flow is going to be different. Now, by the time it comes out, due to this sharp edges, there must be some losses, and due to the end contractions, we call them as end contraction. What is that? End contraction. This flow area will get some minimum and comes to the vena contracta. So at the vena contracta, the velocity is different. That is known as actual velocity. And at the orifice opening, the velocity is going to be different. So from the starting of this orifice to the vena contracta, there must be some loss of the kinetic energy, and how much that loss is nothing but kinetic energy at starting minus kinetic energy at the vena contracta to the actual kinetic energy. So that is known as the coefficient of resistance. Okay, this is just by applying a Bernoulli's principle. I hope you understood how I got this theoretical velocity. So I know the theoretical area of opening means area of orifice, pi by 4 d square, and theoretical velocity as a root of 2gh, and from that I can find out Cc and I can find out the Cv. So by using the kinematics, I have derived what is Cv. What is Cv? X by root of h into 4 into hy. Now you see from here I can eliminate this v square, and this coefficient of resistance can be written as 1 minus Cv square by Cv square, or 1 by Cv square minus 1. Can I write like this? Yes. 1 by Cv square minus 1. Okay. Sir, at vena contracta, as area is less, velocity should be less. No, it's not like that, my dear. Here, the discharge is not going to be constant. See, you are saying that a discharge, when discharge is constant, no, then area decreases, velocity increases. Here, the velocity, you see the CD value. Do you think the CD value is going to be, do you think the CD value is going to be 1? No. You just multiply the CD value over here. What is CV? CC is nothing but 0.62 and CV is going to be 0.95. So 0.62 into 0.95. So if you see this range, 0.62 into 0.95. So this is going to be here the CD range is about 0.59 to 0.62 into 0.99, 0.61. So the range of the CD is a 0.59 to 0.61. So if you keep this much CD, then the CD value, the actual discharge is different than the actual, whatever the discharge or flow rate passing through the orifice. Okay. So now these are the different type of the coefficients, and that's what you need to learn from the orifice. Okay. So I hope you understood this. So these ratios are important, my dear. These ratios are really important. Yes. So now let's see some of the problems. So we got regarding to this orifice. Okay. I'll give you a question. Okay, so now let's write down this question. Okay. Water flows through circular orifice. Water flows through a circular orifice, 25 mm dia. The dia of the orifice is going to be 25 mm in the side of a tank. So on the side of a tank, there is a circular orifice of 25 mm dia, and the constant head of water above the center line. The constant head of water above center line is given as 750 mm. 750 mm, which means H value, and the ordinates of center line of jet are 30 centimeters horizontally from vena contracta, 30 centimeters horizontally from the vena contracta, and 3.2 centimeters vertically below. 3.2 centimeters vertically below the center of orifice. Now, the actual discharge passing through orifice. The actual discharge passing through orifice is 1.186 liter per second. Now the hydraulic coefficients are so whatever the hydraulic coefficients are that may happen, what are those hydraulic coefficients? See, why I have given this question is in this question everything is located. So now you see again we put out the figure. Let's have this figure. So this figure will use a clear idea for us. And you know, when the jump is going to be means when the flow comes out, and the flow is going to be coming out or emerges out, you know that how it forms out in the contractor, and from here onwards the flow is going to be false as an and you know this is known as a vena contracta. So in the given question, whatever the dia, this is nothing but D. So what is the dia I have given? 25 mm. So everything is in terms of centimeters, right? Everything is in terms of centimeters. So 25 centimeters means 2.5. So 25 mm means 2.5 centimeters. And what is the head? Center line. See, the constant head of water above the center line. This is nothing but center line or not? What is H? 7.75 centimeters. So 75 centimeters. Okay. Now, apart from that, the ordinates of the center line of the jet. So from the vena contracta, horizontally that ordinate, the horizontal ordinate is nothing but x value. How much? X value 30 centimeters. Let me represent that as x from the center line. Whatever, this is nothing but the x, and here this is going to be the y. So given x is equals to 30 centimeters and y is 3 centimeters, and the actual discharge passing is nothing but 1.186 liter per second. So the actual discharge is 1.186 liter per second. Okay. So liter per second. So can I write these liters? What is 1 liter? What is 1 liter? 1 liter is nothing but 10 to the power of -3 meter cube. So you can write these liters as a centimeter cube. Yes. No. 1 liter is nothing but 10 to the power of -3 meter cube per second. Okay, fine. We'll do the calculations later. But now you see, I know the dia, I know the height, and I know x and y. I want the hydraulic coefficients. First of all, I'll find out. Firstly, I'll find out the coefficient of velocity. What is coefficient of velocity? X by root of 4 into hy. Okay. So CV is nothing but what is x given? 30 by root of 4 into h value. What is h value? 75 into what is the y value? The y value is going to be 3.2. Sir, in examination, what to do, sir? Sir, in examination, they will give you the values literally to can find. So 75 into 4. What is 75 into 4? What is 75 into 4? 300. So 300. Now, what I do in examination, you see in examination, 75 into 4, 300. 300 into 3.2. Are 300 into 3, 900 or not? 300 into 3, 900. Yes or no? 300 into 3, 900. 300 into 3.2, just more than 900. So how much? 300 into 0.2, which is going to be 60, right? Yes. So this is going to be root of 960, 30 by root of 960. Root 900 is 30. Root 900 is going to be 30. And root 1000 is going to be 10. So, no. Root 900 is going to be 30. 30 into 30, 900. Okay. So now, this root of 960 is going to be more than 30. Then the CV value is going to be less than 1. And how much it is going to be less than 1 now? That's now 300 root of 960 by. So now this value is going to be 0.968 CV. 0.968. 0.968 means let's take it as 0.97. I told you the CV is going to be ranges between 0.95 to 0.98. So let's take it as 0.97. You keep it like that only, 0.968. So 0.968. Yeah. So first I have find out the CV value, and then sir, you know that CD is nothing but CC into CV. So now if I find out the CD value, then I can find out CC also. So already the actual they have given. Now what is our Q theoretical? Q theoretical is nothing but area of the orifice into velocity. Area of the orifice into velocity means root of 2gh. Theoretical velocity, theoretical discharge. Area into what is nothing but T? T is nothing but theoretical, my dear. So now Q theoretical is equals to what is area of the opening? Pi by 4 d square into root of 2gh. Yes. So now let's convert this in terms of meters only. Now, this is a dia means 0.25. Because g value is there, right? What is g value? 9.81 meter per second square. So that's the reason why I'm going to convert this one as a 0.75 meters. 0.75 meters. And this is going to be 0.025 meters. Okay. So see, while converting the units, you have to be very careful. Okay. Now pi by 4 into d value. D value. What is d value, please? What is the d value? The d value is 0.025 square into root of 2 into 9.81 into 750 mm means 0.75. In a ESE prelims, they won't give this much calculations. But I'm giving you this question I'm giving you this question so that you can understand how to solve the coefficients. Okay. So now first find out the Q theoretical. After solving this, you are going to end up the answer as, so I'm giving you directly this one, 1.883 into 10 to the power of minus 3 meter cube per second. So this is going to be, okay, find out this value, 0.025 square into pi into 0.25 into square root of 2 into 9.81 into 0.75. So 1.883 into 10 to the power of minus 3 meter cube per second. Everything is in terms of meters. Now Q actual is given as 1.8186 liter per second, but it can be written as 1.186 into 10 to the power of minus 3 meter cube per second. So because 1 liter is nothing but 10 to the power of minus 3 meter cube. Then what is CD? CD is nothing but Q actual by Q theoretical. And what is the actual? 1.186 into 10 to the power of minus 3 by theoretical. 1.883 into 10 to the power of minus 3. So find out this value. 6 by 1.883. So this is going to be 0.629 as it is going to be 0.629. So it is going to be 0.63. I know the CD value and I know the CV value. So I'll take the CV value as a point, don't convert it directly, because anyways, if you if you are going to take this value here and then the CD value and CV value, CC value is also going to be changes, right? So now I hope you understood how I have solved this. Now, once I know this, then what is CC? CC is nothing but CD by CD. CC is nothing but CD by CD. So what is CD? 0.629 by 0.968. 0.629 by 0.968. So this value is going to be 0.649. So I can take this values as a 0.65 now. Now I can take this value as 0.97. So this is going to be 0.60. The actual values I am taking so that I can find out, my dear, so that I can find out CC value. And you know the CR, what is CR? 1 by CV square minus 1. 1 by 0.97 square minus 1. 1 by 0.97 square minus 1. So this value is going to be 0.0628. So these are the hydraulic coefficients how I am going to solve. And this value, this formula is very, very important. Okay, I hope you understood this quotient of discharges quotient. See, once you understand this, now see, my time is about spending more in the case of the orifice itself. Once you apply this, then the same thing will be applied for the mouthpieces, vias and notches also. I hope you understood this. Any doubt, please? That's the reason why. So one of the student is asking, sir, in examination, so the CV is going to be everywhere. It is going to be less than 1 only. Then how to pick the answers? The range of the CV. What is the range of the CV? What is the range of the CV? 0.95 to 0.99. See, in examinations, the range is going to be. What is the range of CV, please? I said already the ranges. These ranges are important. These ranges are important. What is the CV? 0.95 to 0.99. Okay. So in the case of the orifice, 0.95 to 0.99 means I give the options for the CV 0.85, 0.91 and D value is going to, sorry, B value, C value 0.97, D value as 1. So I'll give the options like this. If I give you the CV value, I'll give the options like this. So it's not in the range, it's not in the range, it's not in the range. The answer is going to be 0.97. Don't worry, you can get that. I don't mean in a prelims they don't give the values to calculate too much. Okay, so don't worry about that. I hope you understood. If you have understood, so let me go for the next. See, I take into the next another level while I was discussing the mains. I am stopping myself for the prelims so that I have to give what is the quotient of resistance, quotient of velocity, what are the ranges, and everything. I have to give these things. Okay, but in the case of the mains examination, I am going to take extra, this one into entire next level. Keep that in your mind. And there is no range of CR, my dear, because it depends upon the CV. There is no range of CR. It depends upon the CV. If you know the CV, see, CR is dependent on CV. Okay. Now, time required to empty tank from the orifice. Time required to empty tank from the orifice. Okay, so now I have given the CD range also. The CD range is going to be 0.59 to 0.61 or 0.62. So generally it's going to be 0.62 only. .59 to 0.62. Okay, so now you please observe. One figure that shows everything very well. Okay, now initially, see, before opening of this, see, you know that there must be some gate like this, then only the water will flow. Okay, before the opening, let's take the water is going to be H1 over here. So let's take this water. Initially, this water is H1 time H1. Now, once I allow the water with respect to time, as the water goes out, this water level will fall from 1 to somewhere here. So now somewhere here, yes or no? But how much head is going to be required? See, let's take this head as 2. But how much time is going to be required to empty the tank from the orifice? See, if I want to empty the tank from 1 to 2, how much time it is going to be take? Now I require that time. So you know that Q is nothing but CD into A into root of 2GH. Root of 2GH. Keep that in your mind. There is going to be CD into A into root of 2GH. So now what I do is, you see here, now observe. Let me take a small element in between while the water is falling out. This is known as a DH. This is known as a DH. So how much amount of the water is falling out? So initially this is H1 and this is going to be H2. So I hope the people who have attended for the geotech, if you have attended for the geotech, have you remembered the falling head permeameter? The people who have attended for the geotech, if you remember the falling head permeameter, there I have discussed. In the case of the falling head permeameter, if you remember, the falling head permeameter, I have derived that whatever the time required to drop. See how much amount of the water is going out, whatever the water. 1 minute. So how much amount of the water is going out? How much volume of water going out? Volume of water releases is equals to quantity of the discharge in the time interval dt. So quantity of the water releases is equal, volume of the water releases is equals to quantity of the discharge in a time dt. So whatever the volume of water goes, so whatever the area here minus A into dH. If A is the planned area of the tank, so if A is the planned area of the tank, now minus A into dH is equals to, means whatever the area of this strip, what is the area of this strip? A into dH. So that's nothing but a volume of water drops. Volume of water drops per unit time is nothing but discharge Q into dt. Sir, why you are representing minus? The meaning of minus is it's going to be false, right? So it is going to be falling. Whatever the water level, how much falling? Minus A into dH. And you know that minus A into, what is area? Keep that right. Into dH is equals to, what is Q? CD into A into, now root of 2G into H. So from the water surface, whatever this level, this is going to be, let's take it as a H. Let's take it as a H. Okay. So 2G into H dt. 2G into H dt. So this water level from here, from the top, this is H1. And from this water level, this is going to be H2. Okay. Now how much water level is falling? Root 2GH. So at that point of time, if the water level falls here, whatever the leftover 2GH, so root of 2GH into dt. Now let's take from here. You take the dt on one side and root comes on the other side, please. Dt is equals to, so here minus A by CD into A into root 2G into dH by root H. dH by root H. So now can I integrate? Now apply integration from 0 to time t. Apply integration from H1 to H2. Apply integration from H1 to H2. Integral of dt t. Integral of dt t. And let's take this as a capital T. Minus A by CD into A into root 2G into. So integral of 1 by root H or H to the power of minus 1 by 2 can I write as H to the power of 1 by 2 by 1 by 2. Because you know that H to the power of minus 1 by 2 plus 1 minus 1 by 2 plus 1. So x to the power of n, integral is nothing but x to the power of n minus 1, sorry, x to the power of n plus 1 by n plus 1. Yes or no? So minus 1 by 2, this is root, right? 1 by root h, right? 1 by root h means can I write as h to the power of minus 1 by 2? H to the power of minus 1 by 2 plus 1 by minus 1 by 2 plus 1. So eventually these are going to be written as h to the power of minus 1 by 2, okay, plus 1. Yes. H to the power of minus 1 by 2 plus 1. So this is going to be 1 by 2, 1 by 2, ranging from H1 to H2. Is it true? Yes. So now minus A by CD into A into root 2G into. So you take this 1 by 2 here, then it is going to be 2A, right? 2A. So this is capital T is equals to Now root of h2 minus root of h1. You send the minus to inside. Then whatever the time required is nothing but 2a by cd into a into root 2g into root of h1 minus root of h2. Root of h1 minus root of h2. So this is the final formula to find out the time required for the orifice to empty the tank. Whatever the time required for the orifice to empty the tanks. So now this is how you need to find out here, right? So after subtracting only, you're going to get that h to the power of 1 by 2 by 1 by 2. Okay. So now this is the time required from here. Whatever the time they mentioned, so sometimes they will give you the time, and the time is going to be 2a by c into a into root 2g. So means they will give you the area where a is the area of tank. Capital A is the area of tank and small a is area of orifice. If you have understood this, then the small difference that I am going to create here is in this pipe, now I am going to provide a tube, and that tube is known as a mouthpiece. I hope you understood how I have been going through this. What is the time required to empty the tank from orifice? So if you know that, then let's see what is a mouthpiece. Mouthpiece. So mouthpiece is a tube connected to orifice. Mouthpiece is a tube connected to the orifice, preferably having a length as 2 to 3 times of dia of opening. So what is the mouthpiece? The mouthpiece is nothing but a tube connected to orifice, preferably having length as 2 to 3 times of the dia of the orifice. So now again the same figure. So in this time, you see, this time I am going to attach a tube. I am going to attach a tube over here. And this tube is known as a mouthpiece. So this is a mouthpiece, and we call it as external mouthpiece. This is going to be the external mouthpiece. This is known as a mouthpiece. So external cylindrical mouthpiece, we said as an external cylindrical mouthpiece, and whatever this tube is known as mouthpiece, and this is the opening arm. So the dia of the opening is going to be d only, and this length is there, right? And here the length, whatever the length of the mouthpiece, let's take that as a L. So that L should not be more than or should be less than or equals to 2 to 3 times of the dia of 2 to 3 times of the D. So every star. Generally, we prefer L is equals to 2 to 3 times of the dia. Okay. Now, what happens in the case of the mouthpiece? See, whatever I said over there, right? Everything again I am repeating back. Please listen. The difference between the orifice and mouthpiece is, now I told you one point over here. While the flow is emerging out from orifice, flow emerging out is not supported by any. So pressure above and below is going to be atmospheric pressure. But now here, whatever the flow emerging out, is having a support of the mouthpiece or not. Now when the flow is emerges out, first it forms a vena contracta. So the flow is going to be forms a vena contracta inside of the mouthpiece. This is going to be the vena contracta. And from here onwards, again, while the jet is emerges out, you see, while the jet is going to be emerges out, this emerges as, so finally, after the vena contracta, the jet is going to be emerges with the same area as the opening. This is going to be the emerging jet. You see, this is a jet. And whatever, this is nothing but vena contracta. Now you tell me, in the case of the here in this portion, if you look over, in the case of the mouthpiece, while the jet is coming out, what is the area of jet here? Now the area of jet is a vena contracta or area of the opening. The area of jet is nothing but the area of opening. So whatever the dia is there, the same dia. So the area of the jet is nothing but the area of the opening. The biggest difference in the case of the orifice and mouthpiece is, in orifice, the flow will contract and then the jet is going to be falls with that area. But in the case of the mouthpiece, this flow emerging out is going to be have a support of the mouthpiece. The flow that is emerging out from the orifice is going to be have a support of the mouthpiece, so that the area of jet is nothing but the area of the opening. So actual area is equals to area of the opening small a, and what is a cc value? Cc is equals to 1. So in the case of mouthpieces, keep that in your mind. In the case of the mouthpieces, the cc is equals to 1. This is the biggest difference. Now you see, and let me look over once again this portion. You observe this portion. Now, when the flow is coming out, there is a vena contracta here. Yes. So now my question is, at vena contracta, now in this vena contracta zone, in the zone of the vena contracta. So you observe over here, flow emerging out, at from orifice has supported by mouthpiece. So the pressure in vena contracta, is need not be atmospheric pressure. The pressure in the vena contracta is less than atmospheric pressure. not as atmospheric pressure. So whatever the pressure inside here is not going to be the atmospheric pressure. So what is going to be happen in the case of the VINA contractor, sir? So what happens over here is now. Yes. Sorry. So now yet to VINA contractor. Yet a VINA contractor. Now at this section here, at a VINA contractor, whatever the pressure acting here, this is a pressure head. Let's take it as a pressure. So absolute pressure is not equals to atmospheric pressure. Absolute pressure is not is equals to atmospheric pressure. So now at a VINA contractor, if absolute pressure falls if the absolute pressure equals falls below vapor pressure. What does it mean by vapor pressure? The pressure at which water starts to vapor. The pressure at which water starts to vapor. If the absolute pressure equals or falls below the vapor pressure, then vapor bubbles will form at VINA contractor. Vapor bubbles will form at a VINA contractor. So you see, you can observe there is some bubbles are going to be formed. Some bubble formation would be there. So when the pressure is going to be less than the atmospheric pressure. So in this case, the pressure means absolute pressure is less than the atmospheric pressure. So if the absolute pressure equals to or falls below the vapor pressure, vapor bubbles will form at the VINA contractor, and that is going to be happen when the head of water is equals to 12.2 meters of water. So what is the head of water here? This is the head of water, right? When the head of water is going to be falls to 12.2 meters, then the absolute pressure falls below the vapor pressure. So whatever the vapor pressures will form at the VINA contractor, where H is the head of the water, where H is the head of the water above the center line, and where H is the head of the water above the center line. So these are nothing but absolute pressures. Understood? Now, let's see about here once again. So as a CC is equals to 1, and in external cylindrical mouthpiece, CV value is going to be practically around 0.82. Around 0.82. So now whatever the discharge is nothing but CV into A into root 2 GH. See, the formula is same. The formula is same, but what is the difference between the mouthpiece and the orifice is the biggest point is this one. So CC. Now in the case of the CD, what is CD now? 0.82. Here the CD is going to be 0.82. And in the case of the orifice, you see, In the case of the RE5s, it is going to be 0.59 to 0.62. Which is going to be more advantageous for us? Which is going to be more advantageous for us? The more advantageous is going to be the mouthpiece. So when I keep the mouthpiece, the CD value is going to be more. So that's about the external cylindrical mouthpiece you need to know. So when does the absolute pressure equals or falls below the vapor pressure? When the H is going to be 12.2 meters of water, and if that head is going to be more than that, then it is going to be safe. If the head of the water is going to be more than that, then it is going to be safe. Okay. So then there are different type of the mouthpieces, and that we'll be discussing after the break. So there are some different type of the mouthpieces. Already it's 8:45. So let's have a break. Let's have a small break and we'll see after the break. So have a break of 20 minutes. So come by 9:05. We'll see the remaining things after the break. Okay, now let's get back to the session. So there are some other different type of the mouthpieces also. So those type of mouthpieces are like types of mouthpieces. So whatever are the type that I have been discussed so far, this is nothing but a external, right? External type, and there is a one more internal mouthpiece. This is also known as a Broda's mouthpiece. Broda's mouthpiece. So in the case of the internal mouthpiece, if this is a figure, now the mouthpiece external means I have provided as outside. Now the internal means so this is the internal mouthpiece. This is the internal mouthpiece. So internal mouthpiece, which means the Vena contractor form here itself, and the jump is going to be means whatever the jet that is going to be goes out, it goes with the same area. So here the CD value is equals to 0.707. See, it's all about changing the CD value only. The formula is same, A into root 2GH, but it's all about changing the CD value only. For RFIs, CD 0.59 to 0.62. 0.59 to 0.62. For external mouthpiece 0.82, and for the internal mouthpiece 0.707. And next, convergent mouthpiece. Convergent So, in the case of the convergent mouthpiece, where is it? Look, in the case of the convergent mouthpiece, what happens over here is the mouthpiece is going to be converging towards bottom like this. The mouthpiece is going to be converges towards the bottom like this. Sir, what happens if I converges over here, sir? Sir, if I converges over here like this, then what happens is the flow will form. So means this is going to be takes care of the vena contractor section. This is going to be takes care of the vena contractor section. So flow is going to be directly enters over here, and then the jet is going to be falls like this. So here, in the case of the convergent mouthpiece, CD is going to be practically 0.975, the largest one. CD is going to be practically 0.975, and there is one more thing known as a divergent. So similar to that, there is a one more thing. Divergent mouthpiece. For the divergent mouthpiece, so now divergent means it depends upon the angles. This is a divergent mouthpiece. So here the CD value is going to be around 0.93. And there is one more thing, convergent divergent mouthpiece. So there the convergent divergent is going to be first it converges and then diverges. First it converges and then diverges. So the most important ones are internal mouthpiece, convergent mouthpiece and divergent mouthpiece. So the formula is same. What I want to say, I want to conclude over here is for mouthpiece and orifice, the finding the discharge is same, but the difference is for the CD value. The difference is going to be the CD value. I hope you understood. So I don't go too much into the mouthpiece because the analysis is same as the orifice. Once you know the discharge, the analysis is going to be same as the orifice. Okay. Now, now let's come to some of the questions regarding to here. I hope you did not got the material. So I will give the questions and then we go for the notches and wears. That's very, very important topic too. So question number one. Question number one. An orifice is discharging under an orifice is discharging under a head of 1.25 meters of water. 1.25 meters of water. A pitot tube kept at its center line yet vena contracta indicates head of 1.2 meters of water. Then the coefficient of velocity is. This is the question. A subject कब होएगा बताएं please. By tomorrow morning will be completed. See, by if we complete this, 50% of the subject will be completed, and we are going to start. I mean, tomorrow also we don't require 2.5 hours. It may take 1 to 1.5 hours only tomorrow. But today I cannot extend the class, as one more class is there for me. So, an orifice is discharging. Anyone is going. College goers are there here? Is there any college goers are here? An orifice is discharging under a head. Okay. Some people are there, the college goers. So I cannot extend the class. Now, solution is, you see again the figure. No. This is vena contracta. So at the vena contracta, I kept a pitot tube. What is meant by pitot tube, sir? The meaning of a pitot tube is to measure the velocity. To measure the velocity. I am going to insert a pitot tube over here. After insertion of the pitot tube, so this is a pitot tube, and whatever the water level rises into the pitot tube and how much it is going to be rises, this is nothing but the velocity head. This is nothing but the velocity head. So that head here, this is a vena contracta, right? Vena contracta means velocity at vena contracta square by 2g is nothing but h. How much they have given? 1.2 meters. And capital H is given as a 2 meters, 1.25 meters. Okay. So whatever this point over here, if you see, so by pitot tube, V actual square by 2G is equals to H is equals to 1.2 meters. Okay, V actual is equals to root of 2GH. Yes or no? V actual is nothing but root of 2GH. So now you tell me what is a CV? CV means V actual by V theoretical. V theoretical. So root of 2GH by capital root of 2G capital H. So here everything will get cancelled. CV is equals to root H by root capital H here. So what is this root capital H? So means square root of 1.2 by 1.25. So square root of 1.2 by 1.25, this is going to be 0.979 something. So answer is going to be 0.98. The value of CV is going to be 0.98. See, if you see the options are, I have given you provided here. Provided the options that I have provided is B value 0.9, C value 0.98, D value 0.65. First of all, I can eliminate A and I can eliminate D. Now in the B and C, 0.9 by 0.98. Yes or no? 0.9 by 0.98 means so 1.2 by 1.25. 1.2 by 1.25 means 0.95, my dear. 1.2 by 1.25 means 0.95. Are a root of 0.95. A root of any value less than 1 will be more than that value or not. If I say root of 0.95, that value should be more than 0.95. I hope you understood. A root of 0.95 means that value, whatever the value, should be coming more than 0.95. Okay. So the answer should be more than 0.95. What is the answer? The answer is going to be 0.98. These are the options that I have provided. I hope you understood. Okay. So now that's about one question, and there is one more question. Water level in cylindrical tank with its axis vertical, with cylindrical tank. So water level in a cylindrical tank. So I have given you the tank with its axis vertical was lowered from an elevation of 4 meters to 2 meters in 200 seconds. In 200 seconds. So in 200 seconds of 4 meters to 2 meters by discharging the contents through an orifice at the bottom. Through an orifice at bottom. Through an orifice at bottom. Okay. Now, if the diameter of the orifice is doubled, now the question it's not there. If the dia of orifice is doubled, the time required for the above lowering of water surface. Above lowering of water surface. See, I have given this much question, but what I am asking you is if the dia of the orifice is doubled, what happens to the time? So options I am giving you as 100 seconds, 200 seconds, 125 seconds, 50 seconds. So solution is, the solution for that is, you know, the time required to empty is nothing but 2 capital A by CD into A into root 2G into root of H1 minus root of H2. So I have given this derivation also. 2A, where A is capital A is the area of the tank. Now which one is going to be doubled? So T is inversely proportional to A, where A is area of a orifice, which means A is equals to pi by 4 d square. Diana. So now can I write as inversely proportional to d square? Yes or no? Now T2 by T1 is equals to d1 by d2 whole square. So T2 is equals to d2 2d by d d2 is equals to d1 is d 2d whole square into what is the T1? T1 is how much? 200. So what is the answer? 50 seconds. The answer is going to be 50 seconds. Answer as a 50 seconds. Okay. Yeah. So answer is going to be 50 seconds. That's it. This is one of the question based upon the RFS. See, these type of questions can be expected for the ESC prelims. In the case of the prelims, these type of questions would be there. And one more question. One more question. So the actual discharge of an orifice having area of 0.0003 meter square and head over center of orifice as 1 meter is dash meter cube per second. Meter cube per second. Okay. Or you tell me in terms of liter per second. In terms of liter per second. And additionally take CD value as 0.6, root 2G as 4.4. So in the case of this is a previous ESC question. Come on, solve it and let me know. What is the answer, please? What's the answer? The answer is going to be 0.792. See, I am asking you the actual discharge of an orifice, which means CD into A into root of 2G capital H. Given area of the orifice 0.0003 and what is the H value? 1 meter. Okay. Now CD value 0.6 into 0.00003 3 into root of 2g. See, root 2g value already given, right? Root 2g value is already given, 4.4 into root 1 into, see, you know, 1 liter per second or 1 meter cube per 1 meter cube is equals to 10 to the power of 3 liters. So multiply with 10 to the power of 3, you are going to end up the answer as 0.972 liter per second. So already I have given everything, the root 2g, whatever the root 2g value is of 4.4, my dear, the root 2g value is going to be 4.4. Okay. Hope you understood this. So I have given one question for finding the coefficients. I have given one question for finding the discharge, and I have given one question for the time required to empty, and I have given one question for the finding one more CV here. I hope you people are able to following me. Now, let's see one more question. So two small orifices A and B of diameters 1 centimeter and 2 centimeters. Two small orifices A and B of diameters 1 centimeter and 2 centimeter respectively are placed on the sides of a tank. Sides of a tank at a depth H1 and H2 below the liquid surface. Below water level. Okay. If discharge through A and B are same. What is the ratio of H1 by H2? Is dash. Take CD values also. CD is a constant. The CD value of the same, both orifices is going to be same. So come on, I need you to find out the answer for this. Come on, solve it. You just see where the changes are happening. I'm saying the same discharge, same CD. The only change is area. Come on, solve. Answer is 16. So those who got 16, that's the correct answer. Answer is 16, my dear. Solution. You know that Q is nothing but CD into A into root 2 GH. CD into A into root 2 GH. Okay. So now I am giving you the discharge is going to be constant. CD is going to be constant. Root 2 is also going to be constant. So here A is inversely proportional to root H. And A is going to be directly proportional to D square. Because area is nothing but pi by 4 D square. Yes or no? So from here I can write root of H1 by H2 is equals to D2 by D1 whole square. So what is the diameter of it? I am giving you 1 centimeter. D2 is 2 centimeters. Yes. So root of H1 by H2 is equals to 2 by 1 whole square is equals to 4. Then what is H1 by H2? 4 square, which is going to be 16. See, you know that Q value, and from there I am writing all these things down. So H square is equals to 16. That's it. I hope you understood this. If you have understood this one now, fine. And I'll give you one more question for you. That I'll be attaching as a question. Okay, I'll give you later. I'll give you the question later because the source that I have is I kept it somewhere. That I'll give you later. So that's about the basic things regarding to the RFIs and mouthpieces. So you can go through here, and the important thing is coefficient and those ranges. Keep that in your mind. Now, there comes notches and VS. See, notches and VS. Actually, notch is a small scale, VR is a larger scale. The definitions and everything is going to be same in notch means whatever the way that we are going to analyze the notch and VR principle to measure the flow rate is same. But notches are used in the case of the laboratory because it is a small scale. VRs are used in the field, means in reality, it's a larger scale. So first of all, what is a notch? So you know that it is a device to measure the flow rate. So where you are going to provide this sensor? So it is a device provided at side of channel to measure flow rate. So it is a device provided at the side of a channel to measure the flow rate. Keep that in your mind, to measure the flow rate. We are going to keep this. So, and where do you see this device? Notch should be placed in a way. The water surface level should be below the top edge. Notch should be placed in a way the water surface level should be below the top edge of notch. Sir, what is the meaning of this one, sir? You see, now let me take a channel. I am saying as a channel, right? So the cross section of a channel, you know, let's say go. So let's take this as a channel. So in the case of the rectangular channel, so let's take this is a water level. Now you observe. This is the water level. This is the water level. See, this is nothing but a channel that I am drawing for you. A rectangular channel. So I said you notch is a device that is provided at the side of a channel. Yes or no? Now, if I cut down a cross section over here, if I cut down a cross section here, so now this is section XX. How does this section XX is going to be looks like? Now in the side view, how does this section is going to be looks like is again whatever this is. This is a notch. So whatever the position that I am giving you here, this is nothing but a notch. Okay. So this is a side of the channel. This is the side of the channel. Okay. This is the side of the channel. So side of channel, and whatever here. So this is and this is nothing but a notch. And you can observe whatever this water level, whatever this water level I am representing you, this is the water level here. This is the water level. So a notch is a device. A notch, this is a device. See, this is a notch. A notch is a device. So where you can see to measure the flow rate. And now in this case, whatever the head of water, this is going to be the head of water, H. I hope you understood. This is notch over here. Yes, yeah, yes or no? So in the case of the channel, notch is a device provided at the side of the channel to measure the flow rate. So if you look over the side of a channel, then this is nothing but the side of the channel. And in the case of the side of channel, this is nothing but the notch. And notch should be placed in such a way the water surface level should be below the top edge. Whatever, this is nothing but the top edge, right? Top edge of notch is going to be this one. Water surface is going to be below that. So generally we used to keep in a laboratory. Okay. So now let's see. So these are about the notch. And what about the weir, sir? What about the weir, sir? Sir, what is a weir? See, weir is a masonry or a concrete structure. Weir is a masonry or a concrete structure over which water flows. See, weir is a masonry or a concrete structure placed in the channel over which flow passes. It's a masonry or concrete structure placed in channel, runs across the flow. Placed in channel over flow, which flow occurs. Over which flow occurs. So generally it has a vertical sides. Generally it has a vertical sides. Okay, so now the weir is a masonry or a concrete structure placed in the channel over which the flow occurs, over which the flow is going to be happen. So now let's see that weir. So this is a channel bed, as we have discussed earlier itself, and we know these things are clearly. This is a channel bed. Now so whatever here, this is a weir, and generally it is going to be a vertical shape, just now I mentioned. And whatever, this is nothing but a sharp crust. So you see, this is a weir, and with what shape? Vertical shape. And is it a sharp crust or a, see, what is mean by crust, sir? Crust means the top of the weir. Crust means the top of the weir or bottom of the notch. See, whatever the bottom of the notch, this is there or not, this is known as crust. Whatever this is a crust. And here, this is going to be the crust. Whatever this is nothing but the crust. I can write this one as a, I can write this as a crust. So what is a crust? Crust is top of weir and bottom of notch. The top of the weir and the bottom of the notch. So now, if you see the cross section, this is a, you see, you can observe. So this is a channel bed, and I told you the weir is a masonry or a masonry or a concrete structure placed on the channel over which the flow is going to be happening. And you know pretty well whatever the analysis we have seen on the upstream and downstream. Now you see, if this is the water level, now once I open the, means on the top there is a crust gate would be there on that. Once I open this, then how the flow is going to be happen? The flow is going to be false like this or not. And whatever the sheet of water, I told you already, this sheet of water is known as a nepe. Yes or no? This sheet of water is known as a nepe. Whatever, this is water level. And this is the water level. Forget about what is happening on the downstream side. I don't care. Forget about what is happening on the downstream side. I don't care. Whether the hydraulic jump happens or no hydraulic jump, I don't care. And you know, whatever this thin sheet of water, you can observe. Whatever the sheet of water that you are seeing here, this is known as a nepe. So here, this flow, this thin sheet of water is known as a nepe. And whatever the water over here also, this is going to be the nepe. Which means, what is nepe? Nepe means a thin sheet of water flows through notch and over weir. So if I say notch through, if I say weir over, so that is known as a nepe, and this is known as the crust point. Okay. So now let's take whatever the head of water above this crust gate, whatever the head of water. This head of water, this is going to be H. Okay. Now, so this time, now let's see the cross section. This is a longitudinal section or elevation, my dear. This is a longitudinal section or elevation. Now, if I see the cross section, have a look about the cross section. Okay. So whatever this is known as a weir, whatever this is known as a weir. So you can see whatever this shape, this is known as the weir. And whatever here, the flow of water, whatever here, this flow of water, and this H is nothing but head. This is nothing but head, H. So where H is a head of water, over weir crust. So now here in the case of the orifice, I took the H as head of water above the center line of orifice. But in the case of the weir, or notch. You see in both the cases, H is nothing but head of water over notch, or head is nothing but head of water over rear crust or a notch crust. Okay. So now you see in both the cases, H is nothing but head of water only, right? So now based upon this, see, this is nothing but a masonry, means a weir, and this is going to be the notch. But notch is the node point here. No. What is that node is a? Notch is a small scale. And weir is larger scale. Notch is a small scale, weir is a larger scale. Similarly, notch is made up of metallic plate and weir is made of concrete or masonry. Concrete or masonry. So that's the difference between the notch and weir. No much difference. In the case of the notch, we keep at the top, and this is a weir. Weir is nothing but a masonry wall or a concrete structure or wall. So placed in the channel, generally it is going to be vertical shape. Generally it is going to be a vertical shape. So now classification based upon this classification based upon the classification of the weirs, you see. We are going to classify the weirs as A, based on shape. Based on shape. Now you see, this is a rectangular weir or not? Whatever are here, whatever the shape, this is nothing but a rectangular weir. The shape is going to be rectangle. Or sometimes it can be triangle also. Sometimes it can be trapezoidal also. Trapezoidal also. Okay. Sometimes it can be rectangular, sometimes it can be trapezoidal also. You see here weir or notch. If I say weir, and that is replicable for the notch also. Notch is a small scale, weir is a large scale. That's it. That's the only difference. So based on the shape, we can say rectangular weir, triangular weir, and trapezoidal weir. Trapezoidal weir. This is based upon the shape. Based on the shape of weir. Okay. Similarly, based on shape of crust. You see here, based upon the shape of the crust. This is the vertical wall which is having a sharp crust or not. This is going to be a sharp crust. Yes or no? So based upon that first one, sharp crusted weir. Second one, broad crusted weir. Third one, narrow crusted weir. And fourth one as ogee shape weir. So you know that in India, most 90 to 95% of the dams are going to be ogee shape only. So what is meant by ogee shape, sir? Whatever in open channel I have given, this is nothing but the ogee shape. Whatever this is a sharp crusted, and this is going to be the ogee shape, and this is going to be the crust, right? So whatever this crust, the top of the weir is nothing but the crust, that is going to be the ogee shape. So this is based upon the shape of the crust. Next, based on end contractions, So what is this end contraction that I will discuss to tomorrow, but just I need to classify this. Suppressed VL, contracted VL. Suppressed VL, contracted VL, based on discharge free falling VL, submerged VL. See, all these are different type of the wears that we are going to see: rectangular wear, trapezoidal wear, triangular notch, rectangular notch, trapezoidal wear. So if I say wear, that is also going to be applicable for the notch. So based upon the shapes and based on the crust, what is the type of the crust we are going to see? Sharp crust. And for our examination, I am going to discuss about the sharp crust and broad crust only. For our examination, we are going to discuss about the sharp crust and broad crust. And suppressed wear, there is a small change. What is the meaning of suppressed and a contractor? I'll tell you tomorrow. So based on the discharge of free falling and submerged, we discuss mostly about the free falling only, not the submerged. The submerged is for the mains. So everything is going to be included into one. Now, how to analyze the wears and notches, that we will see tomorrow. How to analyze this, that we will see tomorrow. Okay. So I hope you understood what is a wear or what is a notch, and the analysis will be discussed in the tomorrow's first 1 hour. So tomorrow the class schedule is 7 o'clock, right? Yes. So I think we may require 1.5 hour, 2 hours. Okay, fine. Okay, let's start with 7 o'clock only. I mean, if it ends early, then fine, no problem. But if we take 1 or 2 hours, then I don't want to go with a hurry. So we'll see. Let's start with class at the same timings only tomorrow also. And tomorrow, yeah, that triangle trapezoidal wear is nothing but the capillary wear. This is known as a hypolatry wear. So tomorrow we'll be discussing the same session. So we'll see how much time it goes. Okay. Yeah. So we'll see tomorrow. Is there any doubts? Yeah, I'll show the notches and photos of the notches and wears tomorrow. It's 10 o'clock, right? Okay. I'll send the PDF also. I'll send PDF today. I'll send PDF yesterday's PDF and today's PDF today only. Okay. So if there is any doubt clearing session, we'll keep the doubt clearing session also tomorrow only, because tomorrow probably we'll end up the class early and we'll take the time for the doubt clearing session. So you please go through the yesterday's class notes and today's class notes today. I will be sharing the yesterday's class notes. And we'll see tomorrow. Okay. Have a nice day. Tomorrow's class time, same class time, same 7 o'clock only. The class timing is same, 7 o'clock only. Okay, fine. Yeah.